Dear friends and followers, welcome back to this follow-up video on how airplanes deal with cold weather. Today we'll be looking at the airplane's onboard anti and de-icing systems and what's that got to do with a plastic water bottle and what makes the Boeing 787 so revolutionary with regard to ice. So let's get started.
1383, runway 27, clear takeoff. United 1538, runway 27, minus way.
A big thank you to Squarespace for sponsoring today's video. More info on what they can help you with at the end. Let's quickly look at which parts of the airplane are prone to ice accumulation. Now, all parts which are directly exposed to the airplane's movement through the air, such as the wing leading edges, the horizontal and vertical stabilizers, the engine intakes, the propellers, pitot tubes, static ports and antennas. And any ice accumulation can lead to reduced controllability, increase in weight and reduce the overall performance of the plane. And icing can occur at temperatures below 10 degrees Celsius and visible moisture. So how do you get rid of accumulated ice on the leading edge of the wing, for example? There are various systems out there which we'll look at in a minute, but most airline jets use the bleed air system. Hot air is ducted via the engine bleed valve from the compressor stage within the engine. The air then runs through a pre-cooler to reduce its temperature to 200 degrees, and this cooled air is then distributed via the bleed ducts to consumers like the air conditioning packs, for example, and the wing anti-ice system. Now, should visible ice be indicated on the visual ice indicator situated on the middle beam of the cockpit windows, you must select wing anti-ice on. The wing anti-ice valve opens up as shown on the ECAM bleed page and the hot bleed air is directed into the leading edge slats 3, 4 and 5. The principle is very similar to your household radiator, but instead of hot water running through the pipes, hot air heats up the leading edge and melts the ice. So the hot air is then guided along the wing through these telescopic pipes into a piccolo tube where the air is distributed through these little holes, warming up the slats and exits via these little black holes at the end. Now you might ask, what about the inboard slats 1 and 2? Why aren't they connected to the wing anti-ice system? Now, as the slat's diameter gets wider closer to the wing root, ice is less prone to accumulate due to aerodynamic reasons and therefore no anti-icing system is needed. Now, the system for the engine anti-ice works very similar. The engine intake very often has this shiny alloy lookalike surface. That's the engine anti-iced area. Again, hot air is extracted via the engine anti-ice valve from the high pressure compressor stage and is piped forwards to the engine intake. The hot air is then distributed through this pipe with these little holes, heating up the intake lip and melting any accumulated ice. And once it's done, the hot air exits via this outlet right here. And the ECAM displays engine anti-ice, and at the same time the turbine ignition system is set to continuous to prevent any engine flame out should a lot of water be injected. Now you need to take special care in case of rapid ice buildup, because as you press the engine anti-ice button, chunks of ice could get sucked into the engine and damage the fan blades. So why not leave the engine and wing anti-ice turned on throughout the entire flight to prevent ice from building up in the first place? The main concern, as so often, is fuel consumption. When you turn on the wing or engine anti-ice, the FADEC increases the engine's power to provide constant pressure to all other bleed air distributors, thus increasing the fuel consumption. Now let's look at other anti-icing systems. Turboprop planes like the Dash 8 Q400, for example, are fitted with the so-called de-icing boots system, which is also based on bleed air supply extracted from the engines, and you can easily recognize these planes fitted with the pneumatic boot system as their leading edges come with a black rubber coating. And once you have visible indication of ice, you actually wait a few minutes to let the ice build up a few layers and then activate the boots. Some of the bleed air is then guided into the rubber leading edge, which expands rapidly and literally breaks up the ice, similar to blowing into a deep freeze squashed water bottle. But why is it necessary to wait before activating the system? Now, in case of only a minor buildup of ice, the boot might only push the ice layer forward, this layer would immediately refreeze, and as the boot retracts, it could leave a gap between the boot and the ice layer, making further expansion ineffective. So further ice buildup could have serious consequences, which fatally happened on an ATR-72 flown by American Eagle in 1994. Why not use hot bleed air like jet airplanes do? Unfortunately, the bleed air output of turboprop engines is not high enough to supply a heated leading edge. But there are some exceptions for this, for instance the Lockheed Electra and the Convair 580, as they have engines with a higher core airflow. Propeller blades are also prone to icing, therefore most of the blade's surface is electrically heated. There is, however, a minor disadvantage. When there is rapid ice buildup, after activating the heating system, chunks of ice could get slammed into the fuselage, and therefore protection panels had to be installed on such planes. Then there is the TKS de-icing system. This uses a glycol-based fluid to cover the critical surfaces of an aircraft, and the fluid is kept in a reservoir tank and is then pumped forward to the leading edge and exits through small holes, so melting the ice. It can also be used to de-ice the propeller blades and windshield, and the system is great for planes within the general aviation category, as most of them don't have a bleed air supply or an electrical output high enough to thermally heat the leading edge. One-third of the system was introduced when Boeing launched the 787 Dreamliner in 2011. For example, the Rolls-Royce Trent 1700 engines are fitted with two high-efficiency generators which produce enough power to electrically heat thermal mats installed within the leading edge slat. The plane was built to be as fuel efficient as possible, therefore has no engine bleed system besides the engine anti-ice. Also, the air conditioning system is electrically driven to reduce the overall fuel flow of the plane. I don't believe I'm actually saying this, but Airbus, you're gonna have to step up your game. And there's one more thing you might have thought that I have forgotten. What about de-icing of the horizontal and vertical stabilizer, as they come in the same shiny surface as slats and engine intakes do? Now, most airline jets don't have heated stabilizers, but during test flights, these jets have to perform flights with 3 inches of ice at the leading edge of the horizontal stabilizer, with no significant impact on controllability. It's just more piping, more weight, more maintenance, more money. And this question is for all turboprop pilots out there: why is your tail assembly fitted with de-icing boots? Please comment below. So to sum up, as you can see, all different systems come with their advantages and disadvantages. But let me assure you, ice on planes is no joke. Do whatever it takes to get rid of it ASAP. And by the way, a classic ATPL theory question is, what's the difference between anti-ice and de-ice? Anti-icing prevents ice from accumulating in the first place, and de-icing sheds build-up ice. I hope you enjoyed this video about the airplane wing and engine anti-ice systems. Make sure to perform a touch and go at my Instagram account, have the engine anti-ice on if there's visible moisture and temperatures below 10 degrees. Don't forget to hit the subscribe button right here, plus the notification bell so you won't miss out upcoming videos. See you next week. All the best, your Captain Joe. Guys, one more thing, Squarespace, being the sponsor of this video, are a huge supporter of my channel, and they are hooking up all my viewers with an exclusive discount and a free trial. I know a lot of my viewers want to be a pilot or want to work in the aviation industry, or just plain aviation geeks. Well, if you want to differentiate yourself from everyone else, build a nice website for yourself, showcase some of your favorite photos, videos, whatever, write some interesting blog posts, showcase info about yourself and your goals, and it's the easiest way to build your personal website. So get the trial and 10% off by simply heading to squarespace.com/CaptainJoe, and I'm looking forward to see your beautiful sites. See ya!